A-level mechanics, dynamics, looking at work. Now in general, when we talk about work, that can mean a variety of different things. However, in mechanics it has a very specific meaning. If we've got an object lying on the floor and we apply a force to it to move it a distance d, we say that the force is doing work on the body. We can say if a constant force F acts on a body and the body moves a distance d in the direction of the force, then we say the work done by the force is equal to the force times the distance moved. In other words, work done is equal to Fd, where F is the force and d is the distance. Now the units of work are newtons times meters, or Newton meters, but they're called joules. Let's look at an example. Consider someone pushing a trolley for 80 meters on horizontal ground, loaded with items weighing 40 kilograms. And let's suppose the resistance to the motion is 3 newtons. We can draw the forces on the trolley and then calculate the work done. Well, first of all, we've got the weight of the trolley and goods. Now that's 40g, acting vertically down. Then we have a normal reaction from the floor acting vertically up, which we can call R. We've got a person pushing the trolley with a force which we can call F, and there'll be a resistance to the motion of 3 newtons. Now if we resolve horizontally, we get F equals 3. The weight and the normal reaction don't come into the equation. Now, because the force F is applied horizontally to the trolley, and the distance moved is in the same horizontal direction, we can say the work done is the force times the distance moved. So we have the work done is equal to F times D, which is 3 times 80, or 240 joules. Now let's consider the same person carrying the same load the same distance. Again, we can mark in the forces and then calculate the work done. There's still the weight of the load, which is 40g, acting vertically down. And the person holding the load is applying a force, we can call it P, acting vertically up. But we see there are no horizontal forces, and so there is no force in the direction of the motion. That means the work done is 0 joules. If you found yourself in the 2 situations above, it would probably feel that the second situation was the more tiring. However, you would have done more work in the first situation. Just holding up a heavy weight feels like hard work. However, if the weight is placed on a table, the table can hold it up without any effort. It's much harder to actually move something. So, to calculate the work done, it's important to remember work done equals force times distance moved in the direction of the force. Now the force and the displacement do not have to be in exactly the same direction, but the force should have a component in the direction of the displacement. If the force is constant, we've seen that the work done on a body by a force is the force times the distance moved in the direction of the force. Consider a body with mass m sliding down a plane under gravity, and suppose it moves a distance d. Now the force of gravity acts vertically down. We can draw that in as mg. Let the angle that the plane makes with the vertical be theta. We see the distance moved in the direction of gravity, the vertical force, is h. So the work done is F times h. Now, if we draw in a triangle under the distance moved and mark in the angle theta, we can see that h is the adjacent side and d is the hypotenuse, and so h is equal to d cos theta. So this gives us the work done is equal to the force times the distance times the cosine of theta, where theta is the angle between the force and the displacement. We can sum that up as work done is equal to Fd cos theta. Another way to look at the situation is to say the work done by a force on a body is the component of the force in the direction of the movement times the distance moved. In the diagram, if the force F moves the object C a distance d from A to B, then the work done is the component of F in the direction AB, which is F times the cosine of the angle times d. So the work done is F cosine theta times d, or the work done is Fd cosine theta, which is exactly the same equation as we had before. So in both cases we see that the formula for the work done is the same. In example 2, we're told a man pulls a sack 80 meters across some horizontal ground using a rope. The rope has a tension of 350 newtons and makes an angle of 40 degrees to the horizontal. How much work does the man do pulling the sack? Well, to solve this, we mark in the tension force. That's 350 newtons up the string. That's at an angle of 40 degrees to the horizontal. And we can show the distance is horizontally 80 meters. Now we've got the work done is the force times the displacement times the cosine of the angle between them. The work done is equal to Fd cosine theta. So that gives us the work done is 350 times 80 times the cosine of 40, which works out to be 21,449.24 joules. So our answer is the work done is 21,449.2 joules, or we could write that the work done is 21.45 kilojoules. In example 3, we're told a bucket of water of weight 12 kilograms is pulled up 15 meters from a well. The rope is light, but there's a frictional force of 8 newtons as it passes over the pulley at the top. Calculate the work done in lifting the bucket. Well, to solve this, on the diagram, mark in the forces. First of all, we've got the weight of the bucket, that's 12G, and then we've got the tension in the rope pulling it up, and we can call that T. Now the rope passes over the pulley, so once it passes over the pulley, the tension will be T plus 8 newtons. Now the bucket is moved vertically 15 meters, so at the top the rope is pulled across 15 meters. Now if we resolve vertically on the bucket, we have T is equal to 12G. As the rope passes over the pulley, there's an additional resistance of 8 newtons, so the force needed to lift the bucket is 12G plus 8. The bucket is raised 15 meters, so the rope is pulled back 15 meters. So the work done is the force times the distance moved. They're both in the same direction. So the work done is 12G plus 8 times 15, and G is 9.8, so that works out to be 1,884. So the work done is 1,884 joules. Consider a block of mass m sliding down a rough plane under gravity. There will be two forces acting on it, gravity and friction. Now the work done by gravity is the force times the distance moved times the cosine of the angle between them. So that's mg times d times the cosine of 90 minus theta. Well, that can be written, the work done by gravity is equal to mgd sine theta. But if we look at the triangle underneath the slope, we see d sine theta is equal to h. where h is the height that the block loses as it slides down the slope. So we can say the work done by gravity is mgh. And this is a general rule. If a body of mass m moves a distance h vertically down, then the work done by gravity to the body is mgh. Now if we consider the work done by friction, the frictional force is up the slope, but the body is moving down the slope, so they have opposite directions. So if we take one direction as positive, the other is negative, which means the work done by friction is equal to minus F times d. So the work done by the friction on the block is minus Fd. However, the block is pushing down against the friction, and so the block is pushing in the same direction that it's moving. So we can say the work done by the block against friction is Fd. So we see we can have negative work done to a block by a force, but this means the block does positive work against the force. In example 4 we have a car pulls a caravan of mass 650 kilograms 60 meters up a gradient of 8 degrees. The caravan has a resistance of 450 newtons. We have to find the work done by the car pulling the caravan. Well, to solve this, we mark in the forces on the caravan. There's the weight of the caravan that acts vertically downwards, and that's 650 G. There's the resistance in the caravan, which is 450 newtons and acts down the slope. There's the normal reaction from the ground, we can call that R, it's perpendicular to the slope. And we can let P be the force the car pulls the caravan with, and P acts up the slope. Now we can resolve up the plane. The plane makes 10 degrees with the horizontal and 80 degrees with the vertical. Now we have one force directly up the plane, that's P, and one force directly down the plane, that's the resistance, 450 newtons. Now the weight has a component down the plane of 650 G cosine 80 degrees, which we can write as 650 G sine 10 degrees. So we get P equals 650 G sine 10 degrees plus 450 degrees, which is equal to 650 times 9.8 times the sine of 10 plus 450, and that works out to be 1556.138 newtons. Now the work done is the force up the plane times the distance, that is P times the distance. So it's 1556.138 times 60, which is 93,368.33 joules. So we can say the work done is 93.37 kilojoules.